Hello there, Mr. Sutton here, bringing you the IM3 Honors 1-5 Extra Practice number 1 solutions on function families and even and odd functions. There's a puzzle that goes with this one. Let's explore that. So for this puzzle, we're trying to figure out whether all of these functions that they've given us here in both formulaic and graphical form are even or odd, or they could actually be possibly neither. And they give us a few tests that we can do at the beginning here. For example, for even, you can plug in negative x and see if it makes your function come out the same as it started with. For odd, you can plug in negative x and see if it negates the entire function that you started with. So we'll be doing some of that as we go, but there's other ways to do it as well that we'll see as we explore these. Now, once you figure out if a function is even or odd, if it's one of those, this is a little bit trickier, but if it's even, you're going to cross out the letter above the function number in this top row here. If it's odd, we have to cross out the letter above the number in the bottom row here. And whatever we haven't crossed off by the end of this, we just write those in here and figure out the puzzle. Now, if it's neither, then we don't cross off anything and we just move on to the next problem. So, with all that being said, let's go ahead and start the first one. All right, for this first problem, we want to figure out if x to the fourth is even or odd. Now, if you have a polynomial, one quick way to tell without doing any other tests that are a little more intense is just to look at the exponents and see if they're either all even, all odd, or a mix. And if they're all even, like in this case we have all even powers, then that proves that this is an even function. So we would go ahead and cross off, let's see here, we need the top row here. We're looking for the letter above 1, which is t, so cross that off. Now, if all the exponents had been odd, then it would have been an odd function, and if it were a mix of even and odd, then it would have been neither even nor odd. For this one, we see that x cubed has all odd powers. There's just one power to begin with anyway, so that means this is an odd function, which means we'll cross off something in the odd row here above 2, which is going to be a c right there. For number 3, we've got negative x squared plus 1. So x squared obviously is an even exponent. 1 actually counts as an even. This is really 1x to the 0 power, which counts as even if we're doing this whole even versus odd thing. So all even powers here. So we're going to use the top row now and cross off the letter above 3, which is r. For number 4, we've got the line 2x plus 3. Since this is a mix of both even and odd exponents, this means we have neither even nor oddness going on here. So that means that we just move on to the next problem. For number 5, we have x to the 5th plus 5. 5 seems to be the theme on this one. This 5th power is odd. 5, this is 5x to the 0, that's even. Since we have a mix of even and odd powers here, this is neither even nor odd. On to the next. For number 6, we have an absolute value function getting thrown into the mix. So for this one, it's not a polynomial, so I'm actually going to try my even-odd test this next time around here. So I'm going to try test for evenness first by plugging in negative x for x. And I'm going to see if that gives me the original function. So I'm asking, is the absolute value of negative x minus 1 equal to the absolute value of x minus 1? And if I have just absolute value of negative x, then that means I could change the sign of this whole expression inside without changing the value, because it's just going to give me a positive output anyway. So I can rewrite this as just absolute value of positive x, and that is equivalent to what we started with. So this proves that it is an even function. We don't have to test for oddness if we get even. So let's cross off in the top row the letter above 6, which is s. For number 7, we're back to a polynomial. This is x to the 1st and x cubed. Those are both odd powers. Since all the powers are odd, this is an odd function. So that's bottom row, above 7, we have this b getting crossed off. For number 8, we have an even power for x to the 4th, and x squared is also even. All even powers means we have an even function. So crossing off the letter above 8 in the top row, that's this f right here. For number 9, we have an absolute value of x plus 1 function going on. Now, the last time I had one of these, it turned out to be even, but I can't really guarantee that that's going to be the case. Also, doing my even oddness test by plugging in negative x here, I'm not really sure how to resolve all that with absolute value. So I'm going to actually go to the graphing calculator and just look at this to see what kind of symmetry it has. So on my grapher, I'm going to go to y equals, and I'll just clear out whatever is already in there. And to get absolute value, one way you can do it is math, and then if you arrow over to number, absolute value, there we go. And then x plus 1 is what I'm entering there. And I'll just do zoom 6, standard window. So there's what that looks like. Now, when I'm looking for even or odd, I'm looking to see if it has y-axis symmetry, that would be even, or origin symmetry, if I rotate it 180 degrees, that would give me an odd function. This has neither of those types of symmetry. It's got symmetry about this line at x equals -1, but that doesn't really get us anything with the whole even-odd thing. So since there's no type of symmetry, at least in terms of y-axis or origin, that means this is neither even nor odd, and it's on to the next. For this one, absolute value of x over x, I don't know what that looks like on a graph. I could graph it on the graphing calculator, but I think it would actually be just as easy to plug in negative x and see what happens. So if I do that, I'm going to first ask if I plug in negative x, does that give me absolute value of x over x? And certainly this top expression here can be turned into the absolute value of x, but this negative x down here, not so much. So those are not equivalent to each other because of this negative x down here. So it's not even. For the odd test, I'm still plugging in negative x, and I'm asking if it negates the entire expression, if I end up with negative absolute value of x over x. So this absolute value up here is still going to give me a positive x. This negative could get transferred to the whole fraction since there's now only one negative in this fraction. And I can write the left side as negative absolute value of x over x. That matches what I thought the right side should end up with if this were an odd function. So this is odd, and I'm going to cross off the letter above 10 in the bottom row, which is right here to this O. Now we're trying to figure out the even or oddness of this square root of x function. So one way you could approach this is maybe thinking of this as, actually you can't really think of this as a polynomial. The exponent would be 1/2, but that doesn't really help us here. So let me just graph this and see a picture of it. I know what it looks like, but I still want to show you all. So square root of x going in my y1. Let me graph that now. Still the same window I used before. And we don't have y-axis symmetry at all. We also don't have origin symmetry because I don't have anything here in the third quadrant. So this is neither even nor odd because we don't have any kind of symmetry. So that's just sending us to the next problem. For this next one, we have p of x equals 5. This is a horizontal line going through the y value 5. Since it's just a horizontal line, it definitely has y-axis symmetry. It has symmetry at every x value, actually. So that means then that this is an even function based off of that. You could also think of this as a polynomial with all even powers. This is really 5x to the 0. In any case, let's cross off a letter above the 12 in the top row. So that's t right here. For number 13, we're back to a polynomial. This is a mix of even and odd exponents. This is really x to the 1. So this is neither even nor odd. On to the next. For 14, we've got the cube root of x to the 5th. I'm going to do my even-odd plug-in negative x test for this one. So if I plug in negative x for x, does that give me what I started with? Well, negative x to the 5th power, we could write that as negative x to the 5th with no parentheses. The odd exponent just preserves the sign that you started with, so the whole thing becomes negative. And then if I take the cube root, odd roots also preserve the sign of whatever you started with. So I could put a negative outside this whole thing and call this negative cube root of positive x to the 5th. Unfortunately, that doesn't match what we started with. So this is not even. However, let's do the odd test here and ask if I plug in negative x, does that give me negative what I started with? And it does. We did all that analysis up here already, right? So we have negative cube root of x to the fifth equals negative cube root of x to the fifth. So this does come out odd then, which means I'll cross off the letter above 14 in my bottom row, which is p right here. Next up, we have x over x squared plus 1, seeing if this is even or odd. Now, you can look at the exponents and see that it's a mix of evens and odds, but that's not a reliable guide when we're dealing with rational functions. These operate a little differently than polynomials in terms of sign rules. So let me do my even-odd test by plugging negative x in for x. So first off, if I plug in negative x, does that give me what I started with? This top part here, the numerator, this is going to be a negative x. Down here, this negative x squared becomes a positive x squared. So we end up with a negative fraction, negative x over x squared plus 1. And that is not equivalent to what we started with, so definitely not an even function. Now how about, is it an odd function? If I plug all this stuff in, do I get negative of what I started with? And we actually did all this analysis up here already. We do get a negative version of this whole fraction when we resolve all these negative signs. So that means this is, in fact, an odd function, which means that bottom row, we're crossing off this t because it's above 15. For 16, we have a very similar problem to 15, but now we have an x squared instead of an x in the numerator. Let me do my even-odd test by plugging in negative x. So if I do that, I end up with an x squared over x squared plus 1. Which is equivalent to what I started with. So this proves that we have an even function. Since it's an even function, we'll cross off the letter above the 16 here, which is this L. For this next function, you might not know it, but we've actually got a semicircle for this weird kind of configuration. And this is a semicircle that is on the origin with a radius of 2. So you could actually graph this out if you knew what you were doing with it and realize that we had y-axis symmetry. However, even if you didn't, you could plug in negative x and see if this comes out the way it started here. If you have negative x squared, that's really just positive x squared that we're subtracting from 4. So plugging in negative x gives us exactly what we started with, telling us that this is actually an even function. So above 17, we've got an s right here, so let's cross that off in that top row. Next up, we have the cosine of x. Now we know that this is a sinusoidal wave type of function, but maybe we don't know exactly what it looks like on the graph, and maybe we also don't know enough trig to figure out what happens if I plug in negative x to this thing. So let's go ahead on the graphing calculator and take a look. So here I am on the grapher. I'm going to go to cosine of x and see what this looks like. And now for my zoom, it doesn't matter that much, but I'm going to do zoom 7 because that gives me a nice little trig window. It's really good for graphing out trig functions like cosine and sine. Now taking a look at this, we see that we have y-axis symmetry. So that reveals that we actually have an even function with cosine. So that means that we're going to be crossing off in the top row this y here above the 18. For 19, we've got sine of x. We did cosine in 18, so my approach here is going to be similar. I'm going to graph this on the graphing calculator. I'm not assuming we've learned how to graph trig functions yet, and we'll see what this looks like. So putting in sine of x, and then using the same window as before, my zoom 7 window. Here's sine of x. We no longer have y-axis symmetry. However, if you were to rotate this 180 degrees, you would get the same shape. So we've got origin symmetry then, which means, since we have origin symmetry, this is an odd function. So we're going to cross off something in the bottom row above 19. Here it is, j. Things are getting a little crazier on question 20. Now we're dealing with sine squared of x. So I'm going to do that on the grapher for sure. So just a little bit of a notation here. This squared means that we're actually taking the sine of x and then squaring whatever that result is. So I'm going to do a parentheses with sine of x inside of it and then close the parentheses. Then I'm going to go back and square that. So that's sine squared of x in grapher form. And let me go now to my graph, see what this looks like. So we've essentially got the sine function, but all of the negative parts of it have gotten flipped to the top here. So this has y-axis symmetry, the way that this is drawn here, which means this is an even function. So let's see here. Even, that means we're crossing off this O above the 20 in the first row. The next few problems, they're actually giving us graphs, which is nice. This graph here, this is some kind of polynomial, but if they give you a graph, you can just see if you've got y-axis or origin symmetry. We've got neither types of symmetry here, so this is neither even nor odd. For 22, we've got this graph going on. It doesn't have y-axis symmetry, but if you rotate it 180 degrees, you do have origin symmetry. It's the same figure. Since we've got origin symmetry, this is an odd function. So cross off something above 22 down here in the bottom row. So that's a D. For 23, we can clearly see that this has y-axis symmetry, at least as best we can tell. So that makes this an even function. So above 23 in the top row, we've got this A that we're crossing off. And now our final problem, 24. It does not have y-axis symmetry, but if you rotate it 180 degrees, you've got the same picture. So that's origin symmetry, giving us an odd function for this. So bottom row, above 24, we've got this K right here. I'm ready to solve the puzzle now. I've crossed off everything I could based on the 24 problems they gave me. So again, the riddle is, what do you call two spheres that are symmetric to each other with respect to the origin? Looking at our leftover letters, in the top row we've got ODD, that's odd. And then in the bottom row we've got BALLS, that's balls. So we have odd balls. They're balls, and it's odd because they have origin symmetry, right? So that's awesome. Until next time, Mr. Sutton signing off.